Next speaker is Filipp Rybakov, who is from Uppsala, and he's going to talk about skyrmions and hopfions and ferromagnetic crystals.
Thank you. And I would say thanks to organizer to give me opportunity to present these results, and it's my pleasure to be here. First of all, I would like to acknowledge my collaborators. It's many people, and the results I'm going to present, it's a kind of synthesis which made possible because of efforts of many people. So many experiments were done in Forschungszentrum Jülich, but also some of them were done in China, in high magnetic field laboratory in Hefei, and also we have a new wave of experiments in SpinX Institute, and there are more. So, okay, so this is the sketch of our plan for this talk. So I will start with purely geometrical ideas, and then we will go more deeply into physics, discuss a lot of experimental and numerical simulations, and we'll end up with purely topology. And to have something in mind, instead of definition, I have the following kind of definition. So magnetic skyrmions are two-dimensional particles made of spins, and hopfions are three-dimensional particles made of spins. Through the talk I will try to establish connection between these two different kind of particle-like states. So let's start with geometry. So no interactions, no physics. Suppose we have given unit vector field in usual Euclidean space, and suppose it's continuous and smooth for simplicity, and we have such kind of setup for this. And if it is given, we can take any point in the space, and the unit vector field denotes certain direction. And so we now suppose we know everything, but what if we interested not in the texture, but locally at every point, we want to somehow quantify the behavior of the field from geometrical point of view, so to give some certain numbers characterizing it. And we can think by analogy. So suppose we have a curve, usual curve in three-dimensional space, that then such local fundamental invariants for this curve. So these quantities are curvature and torsion. So we're very familiar with this one. And what we want to have is something similar, but for unit vector field in three-dimensional space. So it's quite interesting and not widely presented, especially in the physical literature, but will be important for us today. And so these are precisely four scalar quantities listed here, equipped with one vector. So let me briefly name this. So this is the main curvature, which is divergency. Every quantity is, of course, up to some choice of the constant prefactor. So the total curvature, which is product of unit vector with this one. And the most interesting for us today is last two. So this is so-called streamline curvature, which is length of this vector, and non-negative, always non-negative quantity. And the last one is so-called mean geodesic torsion, which is also known as non-halomicity, which is very important for us today. This is M curl M.
So
Filipp, why do you call curl and divergence of M curvature?
Mean curvature. So, yeah, so it has some geometrical origin. You have to restore like a certain surface for which this vector could be a normal. So it's beyond the scope of this vector. Yeah. So okay, what is important for the next step? It's to check which of these quantities are invariants under group of rotations. And so all three are invariant under all three except of last one. So in principle it's clear because we have curl here, and it is invariant only under SO3. And this is nothing else than a quantization of chirality. So this is a whole list of local invariants and only one related to chirality. And so if this guy is 0, so there is no chirality. If it is positive, it is a certain chirality, it's negative. And what does it mean practically? So suppose we have a given unit vector field which belongs to description of some physical system, and for example we find somewhere in the point this quantity to be positive, and it is always there is a certain meaning. So why the chirality is broken? It could be either now explicitly broken or maybe spontaneously. If it is explicitly, probably we're dealing with chiral material. If it is spontaneously broken, so there should be other texture, that the chirality is exactly opposite, etc. So very important quantity. Okay, so just a specific example to have something in mind. So consider Niel type ordering. So presented in two pictures, it's just mirror image of the same. And so this chirality non-holomicity is precisely 0 here. And we have streamline curvature strictly positive for both of the pictures. So actually, geometrically, they are identical because we can simply make a 180-degree rotation of our coordinate frame, and we will see the same, absolutely the same. And the second example is Bloch-type ordering. So the situation here is opposite. So the streamline curvature is 0. And for these two copies, we have this non-holomicity either positive or negative. So this is example of purely chiral unit vector field texture, and this is achiral. Okay, let's move on. Now we will use geometric ideas, but we'll go to our aim from another point of view. So let's make an elementary model of chiral magnet. So we can choose the most basic expression for exchange energy density, which is Dirichlet. It is invariant under O3 and compatible with almost everything, with every crystal, with liquid, etc. So this is a natural step. The second step, we consider crystals with a chiral point symmetry group, such as T group, and we can write all kind of expression of this form, having any projection and any projection derivative with arbitrary coefficient. And yeah, checking all of them, it is simple exercise. We can find that only two forms are compatible with this group. And the first one is divergence, and so it is full derivative. We can integrate it. In a sense, it will transform to some boundary integral if we will assume this is an interaction under Hamiltonian, and only this will survive in the bulk. So we end up with this well-known Hamiltonian, which we also equip with spin orientation anisotropy, which could account for crystallographic anisotropy, or maybe even more important for us, it includes the action of applied magnetic field, which is important to somehow be able to make influence on magnetic texture. So, and yeah, now it's clear that this guy, which we find now is an interaction, it is coincide with a measure of chirality, and it is of undefined signature. Of course, it will refer to be negative in the Hamiltonian, so it's intuitively clear that some chiral texture should immediately follow from this Hamiltonian. Yeah, and we end up with elementary chiral magnetic skyrmion by Bogdanov and Yablonsky. So yeah, and it is just a Bloch kind of rotation in whatever direction. Yeah, so this is the way how we can come to chiral magnetic skyrmion. And yeah, I would remind you the color scheme we will use through my talk. It's a standard one, so black spin up, white spin down, and equator is rainbow colors. Okay, now let's go to physics. So this example of a nice experimental result, so this we published about 7 years ago. And so on the left-hand side, you can see some, let's say, collective behavior of skyrmions, how they can be ordered in a cluster, in a chain. On the right-hand side, you can see a real-time video capture of behavior of just a couple of skyrmions under applied magnetic field. And material is B20 type iron germanium, which is belong to T-point group symmetry. So the typical thickness, it is about 100 nanometers, and this is a Lorentz transmission electron microscopy images, and it's yeah. So the skyrmion we can see either as black or white dot, depending on our focus or depending on a particular chirality of the sample. And the typical size of the skyrmion in iron germanium is about 70 nanometers. And those samples, here you can see the scale bar, it's 200 nanometers. So those samples are typically fabricated from a macroscopic, almost perfect crystal of this type. Okay, so the really remarkable thing about this material is that the situation with skyrmions is not so simple. So there is a lot of things beyond circular shape skyrmion. So yeah, we can check this with our modeling. For example, here I have a recorded movie in the program I designed several years ago and actively used in the studies. So here you can see the so-called grafting method. So what is this grafting method? So what is happening now? So we took a Hamiltonian and discretized it very accurately and made energy minimizer from this model. And this is a program optimized for GPU, etc., with interactive interface. So this is stands for crafting. So with using mouse, we have a list of functions how we can interact with the system, and the basic one, it's either to flip the spins inside the circle or hold everything inside the circle. In this way, we can put program into the pose, draw something, then release, and then you see this thing rotating, the minimization occur, and minimization method is nonlinear conjugate gradient. So with this technique, we actually discovered a lot of stable texture beyond conventional skyrmions. So here in the beginning you can see how skyrmions can be arranged into the lattice, and then I'm cleaning a bit this system and starting to crafting. It is actually a guessing, so not necessarily everything I will draw will be minimized into something stable, but so here especially recorded, so I created the texture I already known be stable. Yeah, so every such bug it's a kind of skyrmion as well. So this is what we can learn from state-of-the-art simulations. And yeah, so this is one of our recent paper which demonstrate a very similar skyrmion bugs again in iron germanium. The issue with this texture in experiment was, it was at the beginning it was unclear how to nucleate them practically, because in real experiment we cannot simply craft, so we don't have such kind of tool. Yeah, but my colleagues designed a tricky way how to do it. So this is yeah. So there are many more of them. This is just a selection. Now we will go by accounting more and more, let's say, the third dimension. So actually, especially in real material, the situation is not so simple because of three-dimensionality. And when we're trying to simulate something, let's say, quantitatively, we have to account stray field effects, so dipole-dipole interaction, and for these purposes, we do more realistic numerical simulation, and particularly I used the form of Hamiltonian written here, which I called third variational formulation of micromagnetics. We proved in this paper. So the trick behind this word, it's right here. So here we don't have a curl of A, but we have a gradient of A. So it's very nice mathematical trick, given the opportunity to write Hamiltonian with stray field, which those structure is organized that guarantee that a statically stable solution is a minima without additional constraint in the form of Maxwell equation. So this is a canonical form, so we can take this Hamiltonian and minimize it directly. And this is very nice for numerical routines in particular. And another interesting thing that, so this is the parameters we use in almost every our work turn out to be very good for B20 iron germanium. So it is of course not of such a precision, it was just a choice, and this model not pretend to account for everything. For example, it does not contain crystallographic anisotropy, it does not account temperature effects well, and a lot of different things, but yeah, we can think it is an effective model, and this parameter works in a quite broad range of temperature, and yeah, it's very nice. So important point, we do not fit in these parameters to explain new observations, so we actually use the same parameters from paper, explaining the textures we had no idea about before. Okay, so now I will list a couple of state-of-art results where third dimension is involved, and we will increase the degree of this significance from slide to slide. So of course, so when we considering situation in 3 dimensions, the skyrmion it form a kind of tube, a skyrmion tube or skyrmion string. Is a simplest generalization to 3D. And this is example of skyrmionium. And in this paper, we actually discovered that this material also have anti-skyrmions. And here you can see that three-dimensionality affect its shape very significantly. And so the way we can present textures in 3 dimensions, so the color scheme is the same, but it is typically enough to draw only the spins which line on the equator on the sphere, on the spin sphere, and this isosurfaces, technique of isosurfaces. Yeah, and this is calculated holography image and Lorentz microscopy image, which we made in the program where I simulated all these things. And this is a couple of slides from experiment. So we are interested in this. So this domain correspond to this one. It denote skyrmion anti-skyrmion pair. So with increasing the field, we observe this continuous disappearing of these two particle and antiparticles. So the next very important example, it's a chiral bobber. So this is this guy. So the idea is that a skyrmion tube not necessarily penetrate the whole thickness. So in fact, it can end up with magnetic singularity known as Bloch point or hedgehog. And this is actually happening in these materials as well. And so this is simulated image, experimental images. So we can recognize this particle because it penetrates not the whole thickness, but partially its contrast is significantly weaker. So it is also kind of particle-like state. The interesting thing that so the Bloch point cost energy, and in conventional magnet, when it is close to the surface, it prefer to escape. Not always, of course, but this is a common idea. But here it is blocked because of this chiral texture on the surface make a kind of potential barrier for this Bloch point to escape. So this is the first principal example that cannot be even approximated by 2D. So if we will try to approximate this texture by 2-dimensional, it's either skyrmion or nothing. So there is no something in between. Okay, the next interesting example is skyrmion braids. So we can have skyrmions in the cluster, but not necessarily to be straight. They can demonstrate braiding. So the braiding is more pronounced in the very thick sample. So we expect that in the bulk they could form almost arbitrary braids. So many of them we calculated numerically. So unfortunately, yet we cannot study experimentally very thick samples because its magnetism, they are not transparent and we are limited. But it is very nice that even in relatively thin or relatively thick samples, braiding still occur and we can recognize it. So this is comparison, simulation versus experiment. And so what is interesting here, because of braiding, so the surrounding of the central skyrmion, it doesn't look anymore as just points, but so they form some kind of, ring. And yeah, so we have such kind of agreement on the quantitative level between simulations and experiments. Okay, and our final destination for today, it's a recent paper on hopfions. So hopfion in the form of rings surrounding Skyrmions rings. And yeah, it was very challenging, and actually we had been studying this material for many years and haven't seen nothing similar before, but finally did it, and this was done in particular because of specially designed field swapping protocol. So in a certain way we enforce the surrounding texture to go inside the magnet, and finally it was blocked by Skyrmion strings, and then we recognized that the ring around it is a hopfion. So how we did it? So we reproduced almost every experimental image with our quantitative simulation, and we find explanation for all these exotic snapshots, and importantly, we did not find any alternative which look like this, but looks differently than hopfion ring in the simulations. So,
Philipp, are these two-dimensional? Are we back? These look like two-dimensional configurations.
but this is images from transmission electron microscopy. So
Sure.
the images are always two-dimensional,
Yes.
but they contain kind of integral of information behind them, and so we can compare images, but the scope of amount of different evidences make a clear conclusion that this is hopfions and nothing
So
else.
it's a thick slab.
Yeah, it is thick, about I don't remember, maybe about 150 nanometers, so thick enough to host hopfion rings. Yeah, but this is of course this is because we are limited in existing state-of-the-art experimental approach, but we can numerically simply make the film thicker, what we actually did, and it turns out that if we are not limited ourselves with thickness and the rest of the thing, we can find many exotic states. So all these are stable solutions in numerics. Okay, so now topology. So it's just a kind of reminder of basic construction for gamotopy groups. So we have a map, continuous map between pairs, and the domain consists of n-dimensional cube, of course, up to gamiomorphism. So sometimes it's conventional to think it is a disk, or maybe it's a whole space with boundary point. And so our codomain is a connected space, not necessarily manifold. And this is a common notation for corresponding gamotopy group, which consists of gamotopy classes of these maps, and the group operation is concatenations of these domains. So we can just join them together, and two-dimensional cubes gluing together, again, n-dimensional cube. Generally, this problem to compute this group for given x is extremely difficult. So what we do have, we have this problem resolved in low-dimensional topology. So for some typical spaces like low-dimensional spheres, there is certain combination through wedges, etc. Yeah, and of course, this is it been solved long ago. So the second homotopy group of the sphere, it's isomorphic to integers, and for third homotopy group of the sphere is also isomorphic to integers. So it's a famous work by Hopf, the one of iconic example of non-triviality in algebraic topology. Okay, So let's pick up several examples from physical systems. So this is examples from different homotopy classes. Sorry. Okay. Yeah. So so the number, it's a charge from this group. So the texture itself, it is some representative for the class. Okay. So we have some examples between Skyrmions and between hopfions. And to take examples, it's not necessarily to consider a specific physical system, because now we are in the field of topology, right? And we can take examples from whatever system and whatever analytical expressions. Okay, so these are maybe more interesting examples. They are from one homotopy class, from the same homotopy class. So what does it mean? So they look very different, but the thing is, because they are from the same homotopy class, we can take whatever pair between these, and there is a continuous path, continuous transformation between them. So, for example, this somehow can be continuously transformed into this and any other pair, and so strictly speaking, an infinity number of other representatives. Okay, so we have for Skyrmions, for hopfions, but what are these? But what are these? It is some kind of combinations, and it's a non-trivial task to classify them. But the simple observation we can do, it seems to be a homotopy group, because we can imagine we can take this sort of cuboid and connect it to this sort of cuboid and then release. So we definitely can have concatenation operation, and of course we expect this group must include pure Skyrmions and pure hopfions as some particular objects when we have a single strings and isolated hopfions. So let's do it. So, and this is the map I suggested for this construction. So we have now domain omega, which is not anymore an n-dimensional cube, but the following construction. So we impose periodicity in one direction, again up to gameomorphism. So it is simply to reflect that we have Skyrmion strings penetrating our domain, and the rest dimensions, it's just some segments. So the omega is I2 cross S1, so this is nothing else than toroid, but solid toroid. Solid toroid, and so the codomain, we have a pair, so X, it's our target space, and for generality, we can take the second component as any contractible space. So not necessarily to consider a point, but we can think there is, so we can soften this boundary condition to, for example, account different modulation like conical phase, which is in fact always presented in our texture easily, because since Y is contractible, we can always apply this contraction when computing homotopy groups. So homotopy classes of this map forms the group, which we denote by G, and this sketch for this concatenation of domains, so for the group operation. So we can join two cubes, not cubes, which is formally now is gameomorphic to solid toroids. But anyway, so we can join them, and then release the boundary, and it will be again the same object from the in the sense of topology. So this cube showing what is happening, let's say magic cube, it's showing what is happening on top and bottom, and something is hidden in the interior. It could be, of course, it's the elongated strings and maybe some hopfions. This is just a sketch to demonstrate the idea. So the group is abelian by construction. And yeah, so because of lack of the time, I will just briefly sketch out the proof, how we derived in the group. First of all, it's identical to the group with factor topology. So because this is contractible, we can shrink the boundary to a point. So we have to take solid toroid and shrink its boundary to the point. And this is a nice relations we can have. So in particular, we can show that this is wedge of 2- and 3-dimensional sphere. And in this way, we can find immediately that the homotopy group is exactly this Cartesian product. And substituting now our space, we immediately end up that it is Z cross Z. So free abelian group of rank 2. And now, so we can compute these charges. This is non-trivial examples which we have from Z cross Z. And this is this number computed with using Kronecker integral and Whitehead integral. And but we can actually compute it, you know, manually, because there is a rule for this particular Skyrmions string. So simple ring, I mean hopfion ring, has its own hop link of value -1 plus 2 links with every string. So that's why, for example, here we have such a huge number. The interesting thing is that braiding also gives some contribution to the hop component. Okay, so, and this is an example of homotopy, so how we can detach one ring through Skyrmions strings in a continuous way. And this is example when we have identity, and we have representatives of the same class. And you can see that hopfion ring here, it's triple twisted instead of once twisted. So it means this linkage is indeed non-trivial. So, and summary. So we have direct observation of hopfions in crystals, seems to be for the first time. Skyrmions and hopfions can form bound states, and together with isolated realization. So we indeed accounted for previously known isolated cases for isolated Skyrmions, isolated hopfions, but generally they are described with this homotopy group. And of course, classification is applicable to other physical systems because it's pure topological. And for example, we can consider nematic liquid crystal and take X is real projective space, and immediately obtains the same group because our sphere is a universal covering, and we use only higher homotopy group to derive this one. So this is the last slide, and thank you for your attention.
Are there any questions?
I lost you at the end. This you talk about relative homotopy groups, but I don't quite understand. What is this Z times Z? Does the Hopf number, and so it's just a product of the two, pi 2 and pi 3?
Yes.
So there's no relative homotopy theory going on, really?
Say it again.
There's no relative homotopy theory going on.
Yeah, here are no relative, but the construction, you know, it's very different. So it is not the common construction for homotopy group at all. So because this domain is very different, it's not isomorphic to the sphere, so our domain is not a sphere anymore. But the result is here. So it is, despite it looks like cross product, so it seems to be, you know, a kind of trivial thing. But in fact, it is, practically, it is indeed untrivial, you know, because we have a kind of linkage between these different structures, and it is involved into these numbers. So, in other words, I would add that when we have only Z, its automorphism group, it is just Z2. So it have a meaning. So because if we dealing with Skyrmions, what does it mean? It's up to our agreement what is positive charge Skyrmion, what is negative charge Skyrmion. The real origin of this kind of duality, it is because automorphism group of integer is Z2. So multiplication with +1 and -1, it's completely isomorphism. So, but here, so what is interesting, so the automorphism of this group is not anymore a finite group. So it's a general linear group with this ring Z under this Z, and it's infinite. So it means we can have infinitely many agreements how to, you know, what to denote zero, what to denote charge. It's not only about sign, etc. So it is not so trivial, I would say.
I agree, but you only have, and these are three-dimensional configurations, so why is pi 2 of x?
It appears because of our techniques involving these algebraic topology arguments. So it is a way how we derive it. So by the way, this group for sphere from exact homotopy sequences also can be derived from something different. So this is just, let's say, algebraic way to derive it.
Small related question. So the order parameter space at the surfaces might be different from the bulk. So then calculating the relative homotopy groups might be relevant and important.
So somehow it is accounted. So as I said, Y here could be any contractible subspace. So for example, we can have a conical face on the boundary. And they can think that it is a top spherical cut. So inside the boundary we have full sphere, on the boundary we have spherical cut. And it is contractible to a point. Because of that, absolutely the same group, so it remains, so it's accounted.
I was curious about your geometrical formulation at the beginning of your talks. You wrote down these 4 invariants, and one aspect was that 3 of them involved a single derivative, but 1 of them involved 2 derivatives. That was a bit of a surprise. Can you comment on that? Yeah, the second one has 2 derivatives,
right.
But the others all have 1 derivative.
Yeah. Yeah, so it's quite complicated theory behind. Yeah, so by the way, it's very important guy, right? So with this guy, we can compute topological degrees, etc. So very well, probably first investigated by Kronecker, even earlier than Hira. Yeah, so it is, this is because, so the overall, the one of the idea behind these formulas is to, because M is a unit vector field, we can think whether we can see this field as a normal to some surface. So in other words, whether we can construct a sort of vibration consisting of surfaces in the vicinity of a given point, and then we can measure how these surfaces, we can apply geometrical arguments to this surface, elementary surface. This is a sort of, and yeah, to measure curvature on the surface, you know, we have to involve 2 dimensions now somehow. This is
the second term.
kind of intuitive argument. This product M with F.
Okay. And if I may also ask, you then wrote down the energy, and the Dirichlet energy is grad M squared.
Mm-hmm.
Is that a linear combination of these?
As I remember, yeah, could be constructed plus boundary integral. Yeah, could be constructed. Plus maybe something will go to boundary integral, and the rest is, yeah, as I remember, yes.
Okay, one quick question.
Okay, very good. So is it always possible that you can realize it as a Gauss map of the surface? Don't you need some kind of hypersurface orthogonality condition to be able to realize it?
The curl is 0.
Yeah, so
But it's I want to do some kind of similar math, but please go on. Then
I'm just a bit confused with the term in terms of mean curvature, total curvature of what?
So again, the arguments to derive this invariance. So there is a solid theory behind this. It is the only thing. It is not, you know, spread in the literature. So there are probably a couple of people who are really interested in this. So it is my suggestion is to think by analogy. So it is somehow quantifying these non-homogeneities. So this is a full collection of knowledges we can extract in the first order quantifying non-homogeneities. Yeah, how to name it, you know, maybe it's not of, it's very tricky, for example, non-halomicity. It's, for example, it means that if we have this non-zero, we cannot restore surfaces. So the origin of this guy is more due to historical reason, I would say. Yeah, probably, of course, it could be done differently.
the fact is that if you see, if you call that mean curvature, means that you are assuming that M is the normal to some surface. So in some sense, it means that this vector M defines the distributions of tangent planes, but then you have to assure by Frobenius that you can that really exists such a surface, and for that you have to assume that something like curl of M is equal to 0, at least curl of M dot M is equal to 0, but this is not good for who is doing
so this is the first criteria for this vibration.
Yes.
What do you mean by, invariant under what? I mean, you call these invariants.
Yeah, this is also for historical reason. So the important word is local. So it means invariant under the choice of coordinate system. So it's really intrinsic. So like with the curvature of the curve, right? So you can consider it in a different coordinate frame, but the curvature is a curvature. So some intrinsic characteristics. In that sense, invariant.
Okay, then let's thank the speaker again.